Our third lesson is estimating larger work items. What happens when we have a bigger chunk of work and all we have is individual expert judgment? Let's take a look. All right, we have our big chunk of work, and we have to say, how can we estimate this using only our memory as calibration? We don't want to do that. Well, what we're going to do is we're going to bring back our old friend, the probability distribution curve, because we know all estimates are actually a probability distribution. We're going to try to fake out this curve. We're going to do this in 3 steps, and this is called 3-point estimation. The first step is to ask the estimator, what do they think? A single point estimate. We know that people, when doing a single point estimate, usually come up with what we call their gut estimate. And we know from a lot of research and practice that the gut estimate tends to be about, here-ish. And we can call that the best case estimate. It tends to be about 25 or 30% confidence level. That is, we look at the area under the curve, 25 to 30% are on the left, 70-ish is on the right. And then we'll say, okay, that's a number. Interesting. But let's pretend that things go wrong. How bad can it be when here at this organization, when everything, and I mean everything, goes wrong? What we're trying to do here is get them off the how good are you question. Single point estimates tend to morph into the how good are you question. Of course, they want to be good, giving us a best case. But if we blame the weirdness of the organization at its most extreme, we can hopefully come up with a worst case. The worst case should be somewhere like way out here. And to do that, I often say, instead of trying to guess that, let's use a multiplier. 3 times, 4 times, 4.5, 5 times. We've seen that some organizations could be up to 7 times or 10 times. This is better if you use your own cone uncertainty multiplier, but a decreed one can work. So we come up with a multiplier. We started with the best case, applied a multiplier to come up with the worst case, and by the way, the worst case should be a very scary number. And then we'll say, okay, great. Let's assume that some bad things happen, but not so many bad things that we got that scary stuff. What's your more likely estimate? They should look at their initial estimate, look at the scary worst case estimate, and come up with hopefully the most likely estimate. It's often close to the highest point on the probability distribution. And now we have 3 points, a best case, the worst case, and a most likely case. This is a good technique to use when we're asked for bigger things, especially when we're being asked to try to estimate schedule or effort directly. We want a best case, a worst case, and a most likely case. We can commit to the range between the best case and the worst case. We'll use the most likely case primarily as a planning tool as opposed to a commitment or a promise. To make sure we're doing this 3-point estimate well, we could up its game just like we do on the individual expert judgment by using a checklist. A checklist structure to say, okay, here's something bigger and we need to answer these questions. Do we understand clearly what's being defined? Does that chunk have a work pattern or list? Are we expecting productivity that's similar to what we've done before? Do we have all 3 points? Is that the worst case really worse? Is the most likely reasonable? That is, we can probably hit it over and over again. Do we calculate an expected case? Oh, that's a new term, expected case. We'll see what that is here in a second. And do I have any wishful thinking like miracles will happen to make this estimate? Using this or a similar list will improve our expert judgment even on bigger items. But what is this expected case thing? The expected case is the name given to something that does some math on top of a 3-point estimate. What the US Navy found years ago was that if I take the best case and I add it to the worst case, and I add 4 of the most likely cases, then divide the sum of that by 6, what happens is I'm going to estimate closer to the true nominal than if I just came up with my most likely. This was part of the Navy's program evaluation and review technique. That's a mouthful. And this calculation is more commonly known as the PERT formula. If we look at the probability distribution, we can see the distance between the best case and the most likely case is way smaller than the distance between the most likely and the worst case. And so anything that takes the average anchored around that most likely, the 4x thing, is going to move it slightly toward the worst case. And that moves us typically closer to a true nominal. We always want to have the true nominal. There's another formula that was popular for a while for doing this, which instead of being a gentle nudge to the worst case, ends up being a big shove to the worst case, the Skutsky formula, and I'm probably pronouncing that totally wrong. I only use this formula if I'm working with a brand new programmers, some interns perhaps. But most of the time, I'm going to be very happy with the PERT formula. All I typically need is a gentle nudge toward the worst case to get a number much closer than nominal. Here we can see a series of 3-point estimates that the PERT was used to calculate an expected case, and you can see it's a gentle nudge toward the worst case. Since the expected case is probably closer to a true nominal, that is what we're going to use for estimate going forward for planning purposes. We are equally likely to be over as under a true nominal. By planning and tracking against this expected case, we hopefully will make any higher confidence commitment that we made. If it's good practice to capture an actual outcome here as well, because again, just like in smaller individual expert judgment estimates, providing feedback will help people make adjustments about how they're doing their inputs into the 3-point estimate. Often, the worst case really isn't worse. Capturing the actual outcome will provide that simple feedback that encourages them to adjust. Actually, also in addition to giving simple feedback with the actual, we can even step that up a little bit with our error calculations. Are we within our estimation art rule of 25%? In this example, we can see that most are in the right neighborhood, but this one, even though this estimator actually was less effort than estimated, it's still a bad estimate that can be improved upon, helping us make better plans. My clients tell me the most common question they get on these mid-sized items is how much effort the work is. Remember, what we want to do is estimate size and then use a lookup or math to get to effort. This is what we want to do to our estimate this way, because if we try to go to effort directly, we can start quickly going wrong. Effort is often a political issue. People want small numbers. We want to give them small numbers. We want to tell them that we're good. All this is political pressure. And if we avoid the political pressure, what is true for my team is not true for other teams. What is true for my organization is not true for other organizations. Effort can vary widely between teams and organization. And of course, we have the diseconomy of scale as well. That as we add people, we become less and less individually productive. A great set of data illustrating how individual productivity lowers as we add people on software development came out of Berlin. This is their data. They found that their average developer, when working by themselves, can produce about 15,000 source lines of code. That's that 15K lock up there. But what happens if we put that individual on a team? They found a formula to describe what happens. If you take their average individual productivity and divide it by the Q root of the number of developers on the team, you'll find the individual productivity as a team member. For example, if they're on a team of 5, instead of doing 15,000 lines of code a year, that same average developer, same brain, same motivation, is only cracking out about 9,000 source lines of code per year. But that same person on a team of 10, now they're down to 7,000. A 50% reduction in their individual productivity. Not because they're dumber, but because they have to spend more time dealing with the diseconomy of scale. They spend time getting in alignment with everyone else to make sure they're building the right thing the right way. We want to be very careful about trying to scale up from how fast I can do it to a bigger team that requires multiple people. It's still better to estimate size and derive estimates. At this point in the classroom, I give the participants a chance to do a 3-point estimate. You can try it too. Read this short case study here. What you do is come up with the best case, a worst case, and a most likely case, and then use the PERT formula to calculate an expected case. The expected case will be our work 50-50, as close to the nominal as we can get. Go ahead and read the story, determine your best case, worst case, and most likely case, and then calculate your expected case to find your 50-50 effort estimate. You can pause the video here and go do it. What did you come up with? What I see when people do this lab is that the best case is often around 130 staff hours. That's what the team did before on something similar. Triad probably won't be better. Some folks think that the case study team could do a little bit better because they've done something like this before. Those folks will come up with the best case around 120. A few times, some participants will come up with the best case around 150 as they see that Triad is similar but bigger. What about the worst case? Well, for the worst case, I hope you chose a multiplier. In the classroom, participants use multipliers for the worst case of 4 times, 5 times, 3 times. I think any of those are defensible. I do see a lot of 2 times, which I don't think is reasonable. The worst you've ever seen is 2 times? I find that unlikely. Your worst case should be really scary, like you want to scream, pound tables, and tremble in your boots. Once you have a multiplier, do the math and come up with the worst case. Next is the most likely case. That allows you to come back to reality from that scary worst case. It should be more than your best case because the best case is, well, a best case. A few things are going to go wrong, and we'll learn some new things, and the scope will probably change a bit. This is a number that estimators are happier saying, yes, I feel comfortable with this number. Once we have our 3 points, we can run the PERT formula and get our expected case. What I find fascinating in the classroom is even though each estimating group has a different best case, a different multiplier, and a different most likely case, the expected cases all come out in the same general ballpark. 4 takeaways from this lesson. First, the 3-point estimates fake out, if you will, the probability distribution curve. We don't know the actual curve, but hopefully we've got 3 key points on it that we can use to make good business decisions. Because those 3 points probably still have some optimism bias, we run the PERT formula, or that other one I can't pronounce. Use that one if you think you have a lot of optimistic bias. More likely, the PERT formula is all you need. We still want to give feedback here because we're still using our memory as calibration. The feedback can help us tune what a good worst-case multiplier is for us. Finally, estimating real effort directly is not a recommended approach. On our smaller tasks, a day or less, perhaps direct real effort estimation can work, but anything bigger, we want to derive effort from size.